Okay, the second part of 9.4, the intersection of three planes, starts with a second case, number two. I've called it in my notes. It might be different in the downloaded classification sheet from the beginning of this chapter, but regardless, we're moving forward and we're looking at this particular case here where we've got two parallel planes and one intersecting plane. Now, this might be the hardest situation to grasp for students here. So I want to, obviously going to solve the system here in a minute, but I want to take a look at just the diagram, okay, for now, for a minute, okay, and, okay, okay, and then these notes here. So two planes are parallel and distinct, and a third plane is intersecting. Now, we know when a third plane is intersecting, okay, it'll be line intersection here, and it's line intersection between, okay, the two planes, and then, okay, so in this case it'd be plane 2 and plane 3, and then line intersection, okay, a different line between plane 3 and plane 1. Okay, so there's no point of intersection for all three, right? The coefficients, okay, are proportional for the two planes, but the third plane, the proportion falls apart here. And the system is said to be incompatible, and when we solve the system, we get a false statement here. So let's jump right in, okay, and solve these. So I'm going to take a look at the normals first of all here. So let me just make this a little bit larger, okay? Okay, so the normal, okay, for this one, okay, is 1, 1, negative 1, and my d value, okay, is going to be negative 1. The normal 2, okay, for the second plane, okay, is 1, 1, 1, okay, and my d value is negative 2. And then the normal for the third plane, okay, is negative 2, negative 2, positive 2, okay, and normal is negative 3. Okay, so to me it looks like it's these two planes right here, okay? I think the connecting statement is negative 2 and 1 equals n3. Now I'm just going to pause there for a second and double check that. So if I take negative 2 multiplied by 1, good, I get that. And negative 2 times 1 is 2. But it doesn't hold for D1, does it? Okay, so clearly, okay, plane 1, and I'm going to use the words here, are parallel and distinct. All right, good. Now, if the second plane, okay, doesn't jive with that, doesn't lie into that parallel and distinct thing, we have to sort of intuitively suggest or think that they must intersect in a line, okay? So they must intersect in a line. So let's consider plane 1 and plane 2, okay? I'm going to go back to my black pen, and plane 1, okay, is x plus y minus z equals 1, and plane 2 is x plus y plus z equals 2. Now, if I add these planes up, what do I get? If I add these planes up, I'm going to eliminate my z's. So I'm going to add, I'll have 2x plus 2y equals 3. And the reason I add these up and not subtract is I'm trying to, okay, look for this line of intersection, right? And if I add these up, I'm going to have my x's and y's. I'm going to rearrange this and solve for x, or should I solve for y? And then I'm going to have 3 over 2 minus x, I think, here, right? Okay, now let's introduce the parameter, okay? So I'm going to let x equal t, so that's going to just change this a little bit to 3 over 2 minus t here. Now, what we've done in the past is, okay, let's substitute it back. We're only considering the first two planes because I'm trying to find that line of intersection, okay, between the first two planes here, just the single line of intersection. So I want to substitute this value back in, okay? So substitute, okay, back into plane 1 here, okay? And I'll get, okay, x plus plus y, okay, but I'm going to let y be my parametric equation, and I'm going to, okay, let minus z equals 1. The other thing I should have did here is instead of x, I could have written t. Okay, so that's okay. Good. Let's clean this up and solve for z here. So I've got 3 halves plus 0t minus z, so there's no t's here. That's fine. 1 minus 3 halves. Negative z would be negative a half, or z equals a half here. Okay, good. Now have I got everything? Okay. I've got x equals t. Okay. Okay. And we know that to be 0 plus t. I've got y equals 3 halves minus t. And I've got z equals a half. And if I would like to write 0t. So as a vector equation, this will be my line of intersection here. That'll be the point 0, 3 halves, and 1 half, plus t, 1, negative 1, and 0. Okay. That's my line of intersection between the first 2 planes here. So I'm going to pause, okay, and do the same process, okay, for planes plane 2 and plane 3 here. Okay? So because I knew plane 2 was my problem plane, right? For lack of a better word. I knew this one wasn't parallel. So I look at plane 1 and plane 2, find the line of intersection, and then I look at plane 2 and plane 3 and find the line of intersection. All right. So let's do this relatively quickly here. Here's plane 2. And here's plane 3. Okay, now I have to, I'm going to multiply plane 2 by 2, right? And I'm going to subtract. Okay, so I'm going to just erase this. I don't need that here. I think I can probably do this in one fell swoop. So multiply this one by 2. Okay, I'm going to have, okay, that might help a little bit better. All right, so now I'm going to go, okay, so 2 and subtract, okay, so that'll be 4x, okay, plus 4y. That's going to eliminate my z's, and I'm going to have 1 here. All right, so let's solve for y. 4y equals 1 minus 4x. X is going to be my parameter, that's why I solve for y. And y equals 1/4 minus x. Or when I let x equal t, I'm going to have 1/4 minus t. Now I substitute in, okay, I substitute it back into 2. Or 1, it's either way. Or 2 or 3, plane 2 or plane 3, and to get this line here. Okay, so let's substitute it into 2. I've got in my notes here. So that'll be, okay, x plus y plus z equals 2. So x plus y plus z equals 2. Well, x I know is t. Y I just found to be 1/4 minus t. And z will be just that. Okay, I've got, okay, plus z equals 2. Z equals 2 minus 1/4, or z equals, okay, I've got 7/4 down here. Okay, so there's my parametric equation. X equals 0 plus t, y equals 1/4 minus t, and z equals 7/4. As a vector equation, that'll be the point 0, 1/4, 7/4, and then t, 1, negative 1, and 0. Okay, there's the second line. Okay, and the one thing I want to point out here is this observation. Okay, look at these 2 lines, these 2 separate lines, if I can find it. Oh. these two separate lines here, okay, they look like they're parallel, so the direction vectors should equal one another. Okay, now I'm just going to size this down. Okay. Okay, and this direction vector was the first one. Okay, and this direction vector was the second one. So that's exactly what we noticed. And see, and like I said, this is probably the hardest case, the most intuitive case here. The others are quite easy. So we'll move on here with, okay, we just did this one. Okay. Okay. And we'll move on to this one. Okay, so let's solve the following system. We've got two coincident and one parallel. Okay, so this is just going to be normals here. Okay, so normal 1, there'll be 1, 2, 3, and D1 will be -1. Normal 2, it'll be 3, 6, 9, and D2 it'll be -3, and normal 3 it'll be -2, -4, -6, and D3 okay will be -2. So in this case, it looks like I've got connecting statements here. 3n1 is equal to n2, okay, and even d1 okay, is equal to, okay, 3d1 is equal to d2, okay, so planes 1 and 2 are coincident. Okay, and what about, okay, what about plane 3 here? I can take a look at my original, okay, I can take a look at my original plane 1 n1 here. So it looks like if I double, okay, and multiply by negative, n1 is equal to n3. Okay, I'm just going to check components, -2, -4, -6, and does the same thing hold for my d1 here? Does that equal d2? If I double it and take the negative of it, I'm not going to get -2, am I? I'm going to get +2. Okay, so I can conclude that plane 1 and plane 3 are parallel and distinct here. I didn't have to include plane 2 in this, okay, in this second part of this example, because I knew that plane 1 and plane 2 were coincident. So I've just shown that plane 3 actually, okay, is apart from, okay, planes 1 and plane 2 here. So that was all. Okay, no algebraic work here, really just, okay, understanding how these normals and D factors work. All right, the last and final case here, this delta configuration is what this is called. Okay, now this is crazy, and I think you're going to have, okay, a little bit of work here, probably in homework example, but the system actually is easy to solve and fall apart here. So we're going to jump right into solving this again, but I want to take a look at the diagram. Notice that any two planes, okay, intersect in a line. So the planes, okay, A and B and C are not proportional. The normal vectors are coplanar, so this little thing holds here. Okay, there's no point of intersection between the planes, and it's an incompatible system, so there's no set solution here. So here's a situation where we've got it here. So I want to take a look at, okay, but as you write these down and look at this system of equations, you notice something right away here, okay, and it's this. Look at that. Okay, those are all the same components. Okay, so if I solve the first equation, okay, and then solve the second equation, okay, let's bring negative x over here, so I have -1 plus x, and then the third equation, okay, would be y plus z. Let's move the x over here, okay, or if I like, don't have to write 0, okay, I can just write -x. Okay, look at what we've got. Okay, we've got y plus z. Okay, so we've got a system here that equals three different things here. Y plus Z equals 1 minus 2x. Y plus Z equals negative 1 plus x. Okay, and Y plus Z equals negative x. Okay, so clearly, okay, there is no one solution here. So no solution. When I've got the same thing equaling three different things, okay, there's clearly no solution here. So it's an inconsistent solution is what we're going to call. And if I actually did, okay, this step here, so I identify my normals, take the cross product if any two, dot it with the third one, and get 0, okay, I'd realize that it was an inconsistent system here. Now I know a lot of students don't like this, okay, so I could stop right here, okay, and identify the fact that, okay, this is not going to lead to a common solution here, okay, but if I did a little differently, I'm just going to finish this one off here by taking a look at plane 1 and plane 2. Okay, so plane 1 is 2x plus y plus z equals 1, and plane 2 is negative x plus y plus z equals negative 1, and I'm going to add, or sorry, subtract these. And if I subtract them, okay, I get 3x, okay, plus 0y plus 0z equals 2, and x equals 2/3. Okay, similarly, if I take a look at plane, okay, 1 and plane 3, so plane 1 I've got 2x plus y plus z equals 1, and plane 3 I've got x plus y plus z equals 0, and if I subtract these, okay, I get x equals 1. Okay, so in this case, by elimination, I get x equals 1, and in this case, I get x equals negative 2/3. So clearly that's, okay, a dilemma, right? A conflict here. X can't be equal to two different things. That kind of was talked about up in here, right? Okay, but here's algebraically how we show it. We reach the same conclusion, no solution. I think we've used the words inconsistent in the past. Either way, we have no solution to this system, okay? And we know that they can't be solved. So that's how you handle that, okay, delta configuration, no solution situation here. There's going to be some homework questions, absolutely. Okay. Oh, let's solve the following system. I think we've got, okay, a couple more to do here. Oh, okay. I'm going to let you guys work through these, okay, as I look for the solution to these. Okay. Okay, this one is the one I just did. That was the last example. Okay, I realized that. Okay, so that was back here, the same one. Okay, I think so. Okay, so we just solved that one already. Okay, this next one I'm going to try and find here and see if I've got an answer to this one. I'm not sure that I do, but looks like I've got, okay, point of intersection, possibly. This may be a homework example. Okay, I'm going to try and work through and find this solution here in a second. Okay, I hadn't done this one, so I wanted to pause it and work through it, and I realized it wasn't that difficult. I noticed it wasn't quite obvious right off the bat, but I noticed that all these three planes are parallel and distinct from one another. The work is there, okay, n1 is equal to negative n2, but the d1 does not equal negative d2, so that's 1 and 2 are parallel and distinct. 1 and 3 are also parallel and distinct. They're connected by a factor of 6, okay, but that same factor doesn't hold for my constant d's. And 2 and 3 are also parallel and distinct. These two planes are connected by a factor of negative 6, but it doesn't, the normals are connected by that factor of negative 6, but that same factor doesn't hold for my d constants here. I have to show each of the three are parallel and distinct. I probably could, each pair out of the total of 3 are parallel and distinct. So 1 and 2, 1 and 3, and then 2 and 3. I could have shown it in a different, maybe more concise way, but this is what I did here for this one. Okay, our homework questions are here, and there's lots of different ones to try and solve. Look at this as a fun challenge. I always like to try and solve the system right off the bat, not knowing what sort of case it is, and then based on what I get for a solution, make my conclusion and try and visualize this. And I would strongly encourage you, if they're given in Cartesian equation form, and they are, that you could go to like 3D Plotter, the website online, and plot these and see these visuals as well. So good luck with this. Enjoy it, have fun. We are almost finished the course.